Start the recording. All right. Welcome to Tuesday. Good stuff. Um, course logistics things. A lot of what I said yesterday still applies. So, um, problem set 5 is out. Problem set for the late due date is tomorrow. So if you haven't already submitted something for it, please make sure to do that as soon as possible. Um, problem set 5. Uh, the second programming assignment was due yesterday. The late due date for that is Saturday. So if you haven't uh, finished that yet, or if you're not happy with your score on that yet, please make sure you get that done. Um, I mentioned that just like for PA1, there's an optional 10% write-up for PA2. Um, so if you want extra credit, a lot of this is like sort of effort based. So um, I think I'll put out scores for the write-up for PA1 within the next day or so. But I think pretty much everyone who submitted something got at least 5% on that. Um, so uh, good way to get extra credit. I also do very much enjoy the fact that like there will be like 2 or 3 submissions for the write-up until the due date, and then there will be like 40 something. Um, And so I always get to tell myself, I always get to delude myself into thinking that it's going to be very easy to grade like 3 write-ups until the due date, and then there's like 40, and then it's not. Um, yeah, you can still turn that in. Um, I guess is a good thing to clarify. Uh, I don't take late days for write-ups, so you can turn that in up until the late day for the programming assignment, and there's no late penalty or anything like that. Um, so just turn that in. Um, exam grading, as I mentioned, is underway. The plan is to have all of them graded before Friday, so we can release those grades to you. Um, and I think that's about it. I think that's all I need to say. That's all I have on my list of course logistics things to talk about. Um, I do have office hours today after class. Um, if you have like specific problem set or PA questions. Um, oh, I said I was going to release PA3 yesterday. I lied a little bit. I will hopefully get that released today. There were some issues with the autograder that we have to sort out. And I don't want to release a programming assignment and not know if the autograder is going to be like if it's going to be possible to have an autograder for it. So I'll release it hopefully today, and either way, whenever it gets released, you'll have a full 2 weeks to work on it. So don't worry about like missing. Don't worry about having like less time to work on it or whatever. Um, yeah, cool. I think that's it. Any any course logistics questions before we start content? All right. If there's nothing, let me pull up a whiteboard. I think. No, that's not what I want. I'm just gonna make a new one. Okay. Great. Okay. So yesterday, towards the end of lecture, I started talking about graphs. It occurs to me that it would probably be good to just start over. Um, so I'll do that. Graphs, incidentally, is my favorite topic of this entire semester, and just in general. Graphs are really cool. So, context, whatever. A graph we can think of as a collection of vertices and a collection of edges, which the edges connect to the vertices, right? So here's an example of a graph. We'll often label the vertices something like 1, 2, 3, 4, A, B, C, D, whatever, right? Vertices can be labeled. Sometimes we will label the edges. Often we will refer to an edge by the pair of vertices it connects. So we might refer to B as like 1, 3 because it connects vertex 1 to vertex 3. More formally, this is the sort of mathematical definition I gave of graphs yesterday. If you go on to take a course in graph theory, or if you dive into more of the theory side of things for any of this, you will probably see this definition come up more often. So I figured it would be good to know. But we can define a graph, and I'll use like a capital G to denote graphs usually. A set V of vertices, set E edges, and a pair of functions st from B to V. You're trying to scroll up. Called source and target, right? So we can see this graph here. The set of vertices is maybe 1, 2, 3, 4. The set of edges is A, B, C, D. These sets happen to have the same cardinality. In general, they might not. And the function S maps A to its source, which is 1. It maps B to 1. It maps C to 2. It maps D to 3. And then the target function maps A to 2, B to 3, C to 3, and D to 4, right? They might not have the same cardinality, right? You could have this is a perfectly valid graph, right? The set of vertices has cardinality of 4. The set of edges has cardinality of 3. Yeah. So this is just sort of the most general sense of graphs. You have a set of vertices, a set of edges sort of floating around in space, and the source and target functions tell you how to glue these things together. We will. Oh, sorry. Yeah, cardinality. I mean the size of the set, right? So there's 4 vertices, there's 4 edges in this graph. But yeah, this is sort of the most. This is sort of the most general way to think about graphs. We will often call these multigraphs because you will also sometimes in the literature see these referred to as quivers, multigraphs, directed multigraphs. And the reason for calling them multigraphs is there's nothing that prohibits like 2 edges from having like this is valid, right? Like I can have 2 edges where the sources and the target both map to the same place. And you can also have like self loops, right? Like a vertex 1 with an edge x, where the source and the target of x are both 1. So all of these are fine for just a very, very general class of graphs. Um, the more specific we get, the more interesting we can make things. So maybe I'll get a bit more specific. So we'll say, um, actually, maybe before I do that, I want to say another sort of adjective to describe these is directed. Because source and target are sort of in general different, right? Like edges, we can draw them as an arrow. They have a direction, right? They go from one vertex to another vertex. Um, sometimes you'll see these abbreviated as like digraphs. Di stands for directed. Um, anyway, so if we have directed graphs, we also have a notion of undirected graphs. Um, an undirected graph is just a directed graph without direction, right? So every time uh, for every edge u arrow v, there is a corresponding corresponding edge v arrow u, right? So for example, if we have, I think the example I used yesterday was this triangle, right? So I have, you know, these edges, and I can draw edges going backwards, right? Um, this I can think of as an undirected graph with just these three vertices, and then I can replace each like anti-parallel pair of edges like this with just a single undirected edge, right? And so I can sort of abbreviate, like I can say that this undirected line, this line without an arrow, stands for a pair of arrows going in opposite directions, right? So we've got the notion of undirected graph. We've got a cycle in a graph. Is, I mean, it's sort of what you expect it to be, but I'll write it down as a sequence of vertices v1 dot 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 vn and edges from vi to vi plus 1 and from vn back to v1, right? So a cycle is a cycle, right? If I have a graph like this, right? And maybe I'll number these vertices 1, 2, 3, 4, right? So I have a cycle here because I have this, right? So there's a cycle here which is like 1, 2, 3, right? Because I have an edge from 1 to 2, an edge from 2 to 3, and then an edge from 3 back to 1, right? So cycles usually make sense in directed graphs because we have this notion of direction between the edges. Um, the idea that there's cycles maybe motivates this next thing, which is a graph G is acyclic if, maybe this is unsurprising, but it's acyclic if it contains no cycles, right? So here is an example of an acyclic graph, right? You'll notice that if this graph was undirected, it would in fact have a cycle, namely it can go all the way around like this. But because it's directed, these arrows only go in one direction. And so I can't like go back up the other way, right? So there's no sequence of vertices that let me like loop all the way around. So this is acyclic. Um, an abbreviation you will often see uh, is DAG, which stands for directed acyclic graph. And a lot of interesting graph algorithms that we'll care about assume that the input graph is a DAG. And a lot of sort of applications of graphs result in graphs that are in particular directed acyclic graphs. So these are a very important class of graphs. We keep doing definitions. Path in a graph is a sequence. Honestly, maybe I should have said path before cycle, whatever. Of vertices v1 dot 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 vn and edges from vi to vi plus 1, right? So a cycle is a path where v1 equals vn, right? Maybe path was easier to introduce first, but whatever. So this is a path. Well, we can say maybe an undirected graph is connected if for every u comma v in its set of vertices, there is a path from u to v, right? A directed graph is strongly connected if that, right? So we use the word connected to refer to undirected graphs. We use the word strongly connected to refer to directed graphs. And the reason is a directed graph like this is connected, right? Because there's like it's connected, right? It's one piece. One piece. In the sense that if you were to sort of like reduce this to an undirected graph, it would be a connected undirected graph. But it's not strongly connected because, for example, there's no way to get from the one piece is real. There's no way to get from this vertex to this vertex, right? Because the arrow only goes in this direction, right? So we can maybe call this like connected, but not strongly connected. Okay. And then I think one last definition for now, although I reserve the right to change my mind. A connected or strongly connected component of some graph G is a subgraph that is connected or strongly connected, and um, what I want to say is maximal with respect to inclusion. But what I'll actually say is like not contained inside any other strongly connected subgraph, right? So for example, um, 1, 2, 3, 4, 5. Um, maybe a question for the chat. How many strongly connected components does this graph have? Maybe we can start with something undirected actually and just talk about connected components. Right, 1, 2, 3, 4, 5. How many connected components does this graph have? Shout out your answer in the chat. Maybe it's helpful if I. You want to say 2, but only 1 is maximal. Ah, okay. Um, it is in fact 2, right? Um, 1, 2. So 2 connected components, right? We've got 1, 2, 3, or the subgraph on the vertices 1, 2, 3, and 4, 5. Now you say only 1 is maximal. Um, when I say maximal, what I mean is maximal with respect to inclusion. So like 4 by itself is not a connected component, even though it's a connected subgraph, because 4 is contained inside 4, 5, right? But the subgraph that looks like 4, 5, here we go. This is not contained inside any larger connected subgraph, right? If I were to try to make this graph larger, it would necessarily become disconnected because I would have to add either 1, 2, or 3, and none of those nodes are connected, right? So 4, 5 is in fact maximal. Maximal in the sense that it can't grow any bigger without becoming disconnected. Does that make sense? Does the difference between, or like does, I guess, does my use of the word maximal make sense? Is what I want to say there. Okay. Um, cool. Okay, so with that in mind, how many strongly connected components does this graph have? And also, what are they? Alternatively, just shout out um, one of the strongly connected components, and then we'll just count up how many distinct ones people shout out. 1, 2, 4. Yep. What else? What other ones? Yeah, you can have a graph that has a vertex and no edges. I assume because you're asking that, you've identified that three is its own strongly connected component, and five is its own strongly connected component, right? Sure. Um, so in particular, three and five do not belong to the same strongly connected component because although you can get from three to five, you cannot get from five back to three, right? Um, so this graph has three strongly connected components, which are these three. Okay, it does have only one connected component though, which is the entire graph because the entire graph is connected. Um, cool. Okay. I guess that's it for graph definitions. Are there any questions about this? I guess I didn't really define subgraph, but maybe I will define subgraph. It's what you expect, right? Um, Subgraph where of so if G is a graph with V and E, its set of vertices and edges, and S and T, the source and target functions, then we can say a subgraph of G is a graph H, and I'll call it V prime, E prime, S prime, T prime, such that uh, V prime is a subset of V, E prime is a subset of E, and S prime and T prime are the restrictions of S and T on E prime, right? So you take a subset of the vertices, a subset of the edges, and you make sure that the subset of the edges map to the same vertices as before. So in particular, this excludes sort of pathological things like if I take this, I can't take like these two vertices, or wait, I can't take uh, these two vertices and this edge, right? This is not a subgraph because this needs to have something on the other end, right? I wouldn't be able to define the other function. I also can't, for example, I can't do like a clever renaming thing like 1, 2, 3, X, Y. I can't end up with like, I can't have my vertex set be 1 and 2, and then my edge set take Y, because now the source and target of Y are changing, right? So a subgraph is just a subgraph, but maybe definitions are nice. Okay. Any questions about definitions before we uh move on? Cool. If there's nothing, let's talk about let's move away from the math and into the engineering, maybe is the thing to say here. We can talk about graph. Oop, that was a bad G. Does graph theory apply to finite state machines? Yes, finite state machines are examples of graphs. Oh, that's such a good point. There was there was a definition that I fully forgot. Okay. Uh a Great. Okay, a weighted graph. um, is a graph G equipped with a function e to, I'm going to say s, right? Or maybe I want to say w, right? Um, do I want to, you know what? I want to call the function w, the sum set s, right? Called the weight. So often in a classical textbook like the LRS, you'll see weights defined specifically as like functions from the set of edges to the real numbers, or like maybe the rational numbers or the integers or something like that. But I think it's important to know that you can weight a graph in any set. And so in particular, a finite state machine um, is an example of a graph weighted by like events that you can read, right? So like if if you've taken discrete math, right? Maybe you know about like finite automata, right? So um, you can think of like this is a start state, and then maybe you can read two different symbols, and then maybe from this symbol you can go here, and then you can visit an end state, right? And so maybe you've got like uh, you read an A or a B, and then you read another B, and then you read a C or something like that, right? And so this is a graph. This is a weighted graph where the weights come from the set A, B, C, or come from like the alphabet that you want to recognize, right? Um, it's in particular also it's a weighted graph augmented with like a start vertex and an end vertex, which is the start state, and maybe a start vertex and a set of end vertices, whatever. Right? I'm not going to talk about automata in this class. You should take discrete math for that. But automata are very cool, and they are an example of graphs. So you can use graph theory to analyze them. A lot of times, though, like when you care about automata, you care about something a lot more specific, or like you have a lot more specific information, and so you can do a lot better than just treating it as a weighted graph. Like you can do automaton specific operations on them, or like finite, like state machine specific operations on them. Um, so yes, oh, maybe I'll just leave this up. Okay, cool. I promise that is in fact it for all the definitions. But again, I reserve the right to decide that I was lying. Let's talk about graph representations. Um, okay, yeah. So there are three um, sort of classes of representations that I'm going to talk about. One is the adjacency list. One is the adjacency matrix. One is the incidence matrix. These all have, these are all, first of all, these are all equivalent in terms of power. So any graph that can be represented as an adjacency list can also be represented as an adjacency matrix, and it can also be represented as an incidence matrix and vice versa. Um, they are, there's obviously like algorithms to convert between them. Certain graph algorithms will expect the input to look like an adjacency list or to look like an adjacency matrix. And so they'll operate on like graph algorithms will often operate on a particular representation of a graph, right? These are sort of like your actual data structure that you have in memory is this adjacency list or one of these two matrices. Um, there's different they have different like space requirements um, that might lead you to prefer one over the other. And oftentimes an algorithm will be more efficient on a particular representation, right? So it's sort of important to know about all of these, know how to convert between them, and know when to use which one. Um, Incidentally, before I forget, the attendance poll for today is going to be uh, telling me the pros and cons of these. Uh, Attendance poll. And this is a very ill-defined question, but it's an attendance poll. So, when might you use one of these over another? Don't answer this now because maybe don't have enough information to answer this now, but over the course of the next like 20 or so minutes, we're going to talk about these representations. And hopefully you'll be able to answer this by the end of class. Okay, so let's start with the adjacency list. Okay. So for this, we keep a we keep an array of vertices. And then of length v, and an array of linked lists of length v, right? Each element in the linked list is a vertex that's adjacent to the corresponding vertex. But I'll show an example, right? So I'm going to, here we go, v0, v1, v2, v3. Here's my graph, perfectly good graph. I've got 4 vertices. So I'm going to start my adjacency list representation is going to have, for starters, an array of length 4 with the data for v0, v1, v2, and v3, right? I might not actually need this array if my vertices don't have any interesting data in them, but oftentimes, depending on where the graph comes from, they will, right? I might want to track something about these vertices. And so whatever my vertex struct ends up looking like is going to end up here, right? Then I have an array of linked lists, right? So this one corresponds to v0, this one corresponds to v1, v2, and v3. And now I notice that v0 is connected to v1. So this linked list has a single node in it, which just holds v1, or it just holds like the index to v1 maybe, right? Because I don't need to hold the vertex again because I can just index into this array. v1 has 2 outgoing edges, one to v2 and one to v3. So this is a linked list with 2 nodes, right? v2 and v3 have no outgoing edges. So both of these are just going to be empty linked lists, right? And so now if I want to look at like all of the like outgoing edges from v1, I can index into v1, or I can index into the first element of this array, which is this linked list with 2 elements, or with 2 nodes. I can reverse this linked list and I can get 2 and 3, and then I can use these to index into my array of vertices, right? And so I can fully reconstruct the graph from this information. Does that make sense? Incidentally, um, if my if my edges have weights, right? So maybe this edge has a weight of 3, this has a weight of 4, this has a weight of -1, right? Instead of just an integer in this linked list node, I can hold an integer and the weight, right? So I could hold like uh, one comma 3, something like that in this node, right? And then here it'll be like 2 comma -1 and 3 comma 4, right? So I can fully reconstruct a weighted graph. This makes sense for directed graphs. Of course, if your graph is undirected, you'll have this sort of symmetric thing, right? So it'll be like V0, V1, V2, V3, and the adjacency list for V1 will also include V0, right? So we'll have like the linked list for 0 will have like a just a 1. The linked list for 1 will have a 0, followed by a 2, followed by a 3. The linked list for 2 will just have a 1. The linked list for 3 will just have a 1, right? So it's perfectly fine for directed and undirected graphs. It makes no assumptions on the acyclicity of the graph or the connectedness, right? You just have a set of vertices and you have a set of edges. This representation is great when the number of so if we talk about the like memory or the space complexity of this, right? Um, who can tell me the space complexity of the adjacency list representation? Let's say in big theta. So I need to store an element in the array for every vertex, right? I have my vertex array. So there's at least a V. Yep, big O of vertices plus edges. So there's the V that comes from here, and then there is one linked list node uh, for each edge, right? For each vertex that's adjacent to another vertex, there's a node. So the total space that I use is big O or big theta of V plus E, right? Um, a bit of notation. Inside big O or theta or omega or whatever, we'll use V and E to refer to the cardinality of V and the cardinality of E, right? This way, I don't have to keep writing out annoying things like big theta of the cardinality of V plus the cardinality of E, right? It's clear that in this context, by V, I don't mean the set of vertices, I mean the cardinality of the set of vertices. Right? So just before you come at me for writing out expressions that don't type check, that's notation that I'm intentionally eliding. Okay, so this is a space complexity. This is nice if the number of edges is relatively small compared to the number of vertices. So we'll call graphs like that sparse, right? So where two vertices are more often than not connected. Um, yeah, so it's good for storing a relatively small number of edges. Or if you have a lot of vertices compared to the number of edges, that's great. If you are going to be adding and removing edges from the graph, this is great because we know how to like linked lists are very dynamic, so we can very easily like if we want to disconnect, for example, right? If I want to take this graph and I want to disconnect V1 from V3, I want to delete this edge, right? I can just look at the outgoing edges of V1, say I don't want it to go to V3 anymore, and just delete this linked list node, right? Very easy to do. Or if I want to insert a new edge somewhere, I can just insert a new edge somewhere, right? If I want to change the set of vertices, I can replace the array of vertices with a linked list of vertices, and I can sort of insert vertices as I want. And then instead of indices here, instead of like one, this can be a pointer into this linked list, or like a pointer to the linked list node for the vertex, right? Maybe I can write this out explicitly. The most like general form of this is we have struct vertices, um, so vertex V, and pointer to the next, right? Um, and struct adjacency, um, what is this? I can say the vertex that I'm looking at, um, maybe a pointer to that vertex for the source, and then no, sorry. The adjacency itself is going to be a vertex for the target, and then a pointer to the next, right? So this is going to be one linked list node, and then the adjacency list is going to be a pointer. Oh, this should be a pointer to the target. A pointer to the source, and then a pointer to the adjacency list. Um, maybe I'll call this like neighbors or something, right? So we can turn all of our arrays into linked lists, and we've got pointers all over the place. This is terrible for the cache. This is, you know, a nightmare to manage memory for, but it's incredibly dynamic, right? I can add a new vertex just by inserting something into this linked list. I can connect that vertex to whatever I want just by inserting into this linked list and then into this linked list. I can connect that vertex to whatever I want by inserting things into this linked list. I can delete a vertex by looping through my linked lists, deleting the things that it's or like deleting the edges that are incident to it, and then deleting it from the list of vertices. I can do whatever I want, right? And the only space this uses up, this is still like big theta v plus e, right? Because maybe there's a 2 here, but we don't care about 2s, right? So adjacency list is great. It's also very simple to think about, right? It's just arrays, arrays and linked lists. We know how to reason about arrays and linked lists. The problem is if I want to ask a question like, oh, and this reminds me, there are definitions that I forgot. Wonderful. If I want to ask a question like, is vi adjacent to vj, right? Given two vertices in my graph, like, is there an edge between them? Or is there an edge that goes from, let's say, v0 to v2 here, right? The only thing I can do is look up the source in my adjacency list, right? So go to v0 here, and then iterate through its linked list of adjacent vertices to find v2, right? So the time that's going to take is on average big theta of e over v, right? Yeah, because on average, I'm going to have to like the average number of edges that any given vertex has is the total number of edges divided by the total number of vertices. Maybe twice that because incoming and outgoing. But either way, the two doesn't matter, and so the average number of things I'm going to have to iterate over is e over v, right? But in particular, this might not be constant time. So our second representation, which is the adjacency matrix, is gonna be designed for constant time determining whether there's an edge between any two vertices or what that edge looks like, maybe, right? So the adjacency matrix is a cardinality of V by cardinality of V matrix, right? We can say maybe the rows represent, or the columns correspond to source. The rows correspond to the destination, right? So for our favorite graph, which I'm going to redraw. By the way, if anyone knows if it's possible to like copy and paste in the Zoom whiteboard, let me know because I would love to. Oh, wow. I see. Did you do that? Oh, that's wild. Oh my Lord. What? This is so cool. Okay. Well, anyway, I've just redrawn the graph. Very much a power move. The adjacency matrix here, we've got four vertices, so it's going to be a 4x4 matrix. The columns are going to correspond to V0, 1, 2, 3. The rows are going to correspond to V0, 1, 2, 3. And we're going to have a 0 if there's no connection and a 1 if there is a connection, right? So let me allocate space for my matrix. And then I can say from 0 to 0, there's nothing. From 0 to 1, we have something. 1 is connected to 2 and 3. 2 and 3 are connected to nothing, right? So here's my adjacency matrix, right? If so, I can of course also just store like my list of vertices, right? V0, V1, V2, V3, right? And then use these to look up things here because my matrix indices just have to be integers, right? If I have data associated to my edges, or if I have weights or something, then instead of zeros and ones, I can have like null and then some struct that represents the edge, or like a pointer to some struct that represents the edge, or something like that. Or I can just have like space for that allocated in the matrix, right? So this is great because we'll say maybe pros. constant time lookup of is V1 connected to V2, right? Because I just go to the corresponding um, entry in my matrix, right? V1 connected to V2. I look right there. I see it's a 0. I know it's not connected. I don't have to traverse anything. I can just directly compute the index that I need to go to and then access that index, like dereference that index. Um, so this is great if the main thing you care about is whether two vertices are connected. Um, the cons, oop, that's the wrong color. Cons are maybe numerous. Um, so first of all, the space complexity is going to be something like theta v squared, because I need an entry in my matrix for every pair of vertices, whether or not they're connected by an edge. Um, or this might be theta v squared plus e, or theta of v squared times e, right? If I'm also tracking edge data, um, then I might have, or no, v squared plus e, um, because uh, yeah, I might have like pointers to edge data allocated somewhere. Um, but either way, often this is going to be much more than just v plus e. If it turns out that the number of edges is roughly on the order of v squared, like if it's a very dense graph, like uh, any two random vertices are very likely to be connected, then uh, theta v squared is not going to be that different from theta v plus e, right? So it's maybe not as bad to use an adjacency matrix from an asymptotic perspective. Also, if there's no like non-trivial edge data and all I care about is whether two things are connected or not, the coefficient in front of here can be very nice because I only need one bit to represent each of these, right? So it won't be a nice like matrix because you can't it won't be a nice array because you can't index at like sub-byte precision, but you could like pack a bunch of this together, right? So a 4x4 matrix you could fit into just 2 bytes of memory, right? And then you could do your like bit manipulation to figure out whether two things are connected. So it's possible to make this very space efficient. And if you already have a lot of edges, uh, there's not like you're not getting much benefit from using an adjacency list anyway, right? And you get this sort of constant time lookup of whether two things are connected. Um, Cons, space complexity. Another con is it's very difficult to like uh, to resize, right? So inserting and deleting edges is easy because I just write to the corresponding position in the matrix. If I want to connect two vertices that weren't connected, I just write a 1. If I want to disconnect them, I write a 0. Inserting a new vertex is terrible because it means I have to reallocate an entirely different array with different dimensions and copy everything over and then like do this stuff with a new vertex. If I want to delete a vertex from the middle, God help us all, right? You have to reallocate everything. Um, Finally, in the last like minute or so, I'm going to talk about the third one, which is the incidence matrix. Fortunately, I don't have much to say about this. It is my personal favorite matrix representation, but it shows up very infrequently in graph algorithms. It shows up a lot more in like math, like graph theory. And there's good reasons for that that I won't talk about right now. But the incidence matrix, usually abbreviated with this capital phi, um, has we'll say like columns correspond to, what do I say, edges. Um, Rows correspond to vertices, and B of E V is 1 if the edge leaves the vertex -1 if it enters, and 0 if it's not incident. Right? So here, I had 0, 1, 2, 3. Maybe I'll name my edges X, Y, Z. So I would have X, Y, Z across here, 0, 1, 2, 3 down here. And then X goes from 0 to 1. Y goes from 1 to 2. What am I doing? Nope. I don't know how I drew this box, and I don't know how to get rid of it, so pretend it's not there. Z goes from 1 to 3. Right? Keep doing this. Okay. And so here you go. Right? Of course, in an incidence matrix, if you want to see if an edge is incident to a vertex, you just look up that column and you like find what it's incident to. But this requires you to like know the number of edges and the number of vertices in advance. This very rarely comes up. Most of the time, we're going to be talking about these first two, the adjacency list and the adjacency matrix. Okay, that's all for lecture. There is an attendance poll. Please fill that out. I have office hours starting, I guess, morally speaking, starting now. So if you have any questions, I am happy to answer them. I'm going to pause the recording.